Hi everyone. So today we will be covering the second part of transformers in AI. The last video we went through motivation, like the attention mechanism, how it works, self-attention, multi-hit attention, and all that was to prepare us to move forward and learn more about transformers. So today we'll see the architecture of transformers, how they work, and maybe we will focus on transformer-based language models. So in this uh, uh, example, we will study two transformer-based language models. The first one is GPT, and second one is BERT. Mainly, we will focus on the difference between them and how we use transformers for language model. And then we will dive into again generative AI and understand the mapping, where do we stand today, foundation model, language model evolution, and we will talk about LLMs. So mainly this is a summary of what we did last time, so in the previous video. So like I mentioned, when it comes to transformers, so the entire architecture is built around the idea of attention, and in particular self-attention and multi-head attention. These two mechanisms covered in the last video are what make transformer powerful and efficient. Just to summarize again, so self-attention is a core mechanism that allows the model to evaluate how important each word is relative to the other when encoding a given word. And it captures relationships across the entire sentence without relying on recurrence. For multi-head attention, so this extends the idea of self-attention by running multiple self-attention operations in parallel. So each head focuses on different types of contextual information, and this enables the model to build richer and more expressive, let me say, representation. So transformer architecture fundamentally relies on self-attention, multi-head attention to process input sequences efficiently, and to capture both local and global dependencies. So now when it comes to transformer architecture, as I mentioned earlier, it is fundamentally built on the attention mechanism. So instead of, I again come back to the same example of CNNs. So instead of, stacking layers the way we do in CNN, such as for example, convolutional layers or max pooling layers or um, fully connected layers and so on. So the transformer uses blocks, okay? So as you can see in this architecture, so the blocks look like this. So mainly we have our input and we have our output, and we have a repeated internal structure, okay? So we can stack as many as of these blocks as needed, okay? So it's not a rule only to have this, you can add as needed, okay? And this mainly depends on the model size, okay? So the first now component inside this block is the self attention, okay? And self-attention mainly, let me say, it processes, let's say, the relationship across the entire sequence. After this, we find the layer normalization. And layer normalization here, let's say, normalizes the output from the attention mechanism to stabilize and improve training. After normalization, we find MLP. So we apply a feed forward neural network, and this allows the model to transform the representation further. Okay, and so again, as I mentioned, you can use as like many like blocks as you want. So now the architectures often chain together multiple transformer blocks like we seen here. Okay, so we can see different designs, but mainly these are the blocks. For layer normalization and residual connections, so the main like reason of introducing them here, so they improve training. Okay, so it make it, for instance, like faster, and it can lead to better results. And now for the MLP component, okay, you see the forward layer per input here. So you are already mainly familiar with feed-forward neural networks applied to each input representation. So after the MLP here, we apply another normalization layer to stabilize the output once again. So as mentioned earlier, we can like stack as many transformer block again as needed. So I always, whenever I teach architecture to my students, so in deep learning, I tell them now I'm teaching you the components. For example, in CNNs, the components are convolutional layers. We have another component, the pooling layer, another component, maybe the dense layers. I tell them these are the components, and you are the architect. You are the designer. You are going to create, and it's like you have the puzzle. Now show me your creativity by introducing let me say the best architecture ever. So this is what researchers mainly do. So these are the, I would say, basic building blocks, and using this we can build further. Okay, so this is the idea. Now the question, let's say, that is, where do we introduce nonlinearity in this block? So we usually talk about nonlinearity when it comes to neural networks, and it's extremely important. So the question is, in this block, like, where do we introduce them? And mainly the answer is like any like traditional neural network. So nonlinearity is mainly introduced in through the activation functions. Like for example, we have softmax. Softmax is the activation function that introduces nonlinearity when we convert raw attention scores into probability values. Okay, so it's very important to mention. But this is not the only one. So that's not the only source of nonlinearity, because within self-attention, okay, mechanism, activation functions appear in several internal steps as well. Okay, you have also the MLP, and the MLP also introduces nonlinearity, and that's mainly through the feed-forward activations. Also, we can like say that the layer normalization contributes mainly to the nonlinearity and transforming the representation into nonlinear, in a nonlinear way. So normally in a transformer block, like comes the nonlinearity mainly comes from self-attention, activation functions there, the MLP component, and the normalization operations. Okay. So the challenge with this architecture is that it introduces certain limitations. So since we are working in the domain of NLP and our input consists of text, I mean sentences composed of tokens, like for example, hi, how are you? Each word can be considered as a token. So here, hi, for example, is a token, how is a token, are is a token, and you is a token. Okay, so this issue arises when we consider the order, okay, which is very important in a sentence. So considering the order of these inputs or input words can create some problems. So just to let you know, transformer block on their own do not like account for order, okay? They don't consider word order, and this becomes a problem because, let me say, the meaning of sentence in natural language depends heavily on like the sequence of words and how these words are like let me say ordered, okay? And this is like maybe one disadvantage, but there is one advantage. So however, even if the model receives, like, let's say that the model is receiving the uh, words in like disorder, like are, how, you, how you. Okay, so not how are you, so are, how, you, not like in the right order. The output still is going to respect this like disorder, which is something good after all. Okay, so this consist like this is the good thing, okay, let me say, okay? The model, if he receive the input in like incorrect order, it will still process them consistently, meaning that the input order is, even that it is incorrect, the output order will still reflect the same incorrect order of the input, okay? So by consistency, like the problem related to this consistency does not solve it. Again, the underlying issue that transformers themselves are, let me call them ordered, okay? They are order agnostic. So the question becomes, how do we handle this kind of limitation, and how can we probably introduce this kind of information, the information concerning the order of a word into the model. So the solution is to keep track of the position of each like token, and to do this we introduce position embeddings, okay? And position embeddings are learned during training on sentences and that are having varying lengths. So now, in addition to the standard input embeddings, we also like incorporate what we call positional embeddings. Okay, so the idea here is like just to recall that token can like, for example here, je suis étudiant. So here we have three tokens. Je is a token, suis is a token, étudiant is a token. And now the token cannot be fed directly, like I said last time, into the model. We need to embed it into kind of, we produce from this like text some numerical representation. And now this numerical representation is going to be fed to the encoder. Okay, so how to embed or generate this like vector? It's like we said last time, we can use whether RNNs, we can also use LSTMs for this purpose. Okay, so once we obtain now the embedding, let's say for a token like je here, so we do not feed it alone into the like block, okay? And so how what do we add? So here we add the positional embedding, okay? So it's the information like about the position, okay? And so this indicates whether the token is first, second, and third, and so on within the sentence, okay? And so we do the same for all our tokens, okay? So this is mainly the idea. So here another probably type of positional information, we use positional encoding, okay? Positional encoding is a function that maps each position in the sequence to a vector that the network learns to interpret. So this mainly enables the model to generalize the sequence length that may not have like appeared during the training. So this is the basic idea of like how we assemble the block or layers that transform that are in a transformer block. Okay, so the block mainly is nonlinear because it contains softmax within self-attention module. So we also have the normalization layer, and these both introduce the nonlinearity. So one limitation now of transformer is like that it does not naturally encode the order, but this issue now is resolved by adding the positional embeddings and the positional encodings, which inject the notion of first, second, third, and order into the representation of each token. Okay, so now let's explore the first major work that introduced that has been introduced or in the literature, and that introduces mainly the idea of attention. So the breakthrough paper in this case is attention all you need. You might hear about this paper before. So before we walk through the model architecture, let me quickly show you mainly how to find the paper properly. Okay, so because when you are searching for papers, I don't know if many of you did this before or not, but it's very simple. Just you go to Google and you write you go to Google Scholar and you try to search in the right place. So if you're searching for scientific article, Google Scholar, you can search for it. So here, attention is all you need. This is what I'm writing. And see here, so this is mainly the paper that we are looking for. Oh, and you see here the citations. It's like exceptional for a paper. Okay, so now once we found our paper, because see here, the citation is like 200K plus, but usually people like cited 13, 24, 50, 100 of times. But this is an exceptional work that is making the big change. So let's open, whether if you want to download this paper or if you want, you can just open it and in your browser. Okay, so this is mainly the paper. So please just pause your video and try to find this paper on your own, because mainly you are going to go through this paper as well. So it's a very important paper and I want you to go through, please. Okay. Okay. Let's suppose that everyone is now having in the paper. Okay. How to go through the paper? A very important question. Now you will see that it's 11 pages and so on. Don't worry about that at all, because it's very simple. So the main thing that you're going to read the title, attention is all you need. So next, mainly you go through the abstract. So you now will read the abstract. Once you read the abstract, you will get an overview, an idea about the research paper. Mainly it will introduce you to the topic, if like some problems in the state of the art or some gap exists, what is the value that this paper adds to the existing works. Then okay, this is the idea and it's coming to fill this gap. So what are the results and the achievements of this model? So mainly these are the main points discussed in the abstract. Next, now you go through the introduction, which I recommend because it will make you understand the context. So understanding the context also can lead you to the main like contributions, let me say, of this paper, and you will understand this as well, okay? So no need to go through background. I mean, for someone who's reading for first time, next you can reading a paper can not only take 10 minutes, so it can take you even 10 days. That's very normal. But now what I mean is that we are going just to go through the paper. So after reading abstract introduction, you just go through the paper. So stop by if any figure that, especially first figure, is usually summarizing or illustrating the idea. So this is mainly the transformer model architecture. So you try to take some time, take a look on this like architecture. Try to understand from the visual representation. If clear, then perfect. Otherwise, try to find wherever like this like figure one is referenced in the text. So like that, you can only read the parts where it's talking about like figure one, or here, for example, figure two, and you go through the figures to try to understand what's going on. Okay, now your job is done. You are going to jump into the conclusion. So this is what you will do in the 10 minutes. Conclusion you will read. So if there are some points you are missing, you didn't maybe capture from the introduction, main figures, and like some portion of the text that you are paying attention to, you're using your own attention mechanism to understand. So you will maybe find in the conclusion. So like this, you are reading the paper in 10 minutes, getting an overview. From the conclusion, now you'll understand the important points and you can come back and focus on that particular part. Otherwise, like you can like go through the paper very well and take your time for that, okay? But I'm just showing you how to do that very quickly. So now what you will do is that you're going to pause the video for exactly 10 minutes. I don't know if you want to put a timer or I keep the video recording for 10 minutes. I think it's not a good idea. So I would rely on you to put a timer. And after 10 minutes, you just keep like come back to the presentation and recording because I will mainly go through this paper, okay? So thank you very much. Now let's look at the very first use case that made transformers famous, okay? For especially machine translation. So in the pioneering transformer model, what we have is mainly two components. We have the encoder, which process the input sentence like je suis étudiant here, and then we have the decoder, which generates the output in this case, like I am a student. Okay, so the encoder mainly what he does is that he reads the entire sequence. Okay, he captures its the meaning. Okay, and then pass the rich representation to decoder. Now here the decoder uses this information to produce the translated sentence. So one token at a time. Okay, so this encoder decoder like architecture or structure is mainly the foundation of the original transformer like architecture. Okay, so as you can see here, this figure from the paper, the overall architecture has like two main blocks, so the encoder and the decoder. Okay, so and both of them mainly now rely heavily on self-attention and also multi-head attention. So each side here is like kind of built from 6 stacked layer, and at the bottom now what we will start with is mainly a positional like encoding, which injects information about the order as well. So within like each layer we have multi-head attention, okay, and this is followed by MLP, like multi-head attention, then like add a norm forward, feed forward is the MLP part. Okay, so maybe you will also notice this kind of arrows. Okay, I would say the jump means that these are what we call skip connections, okay? And so these are the arrows that mainly skip over entire layers. And so these are also called as residual connections. So they act like, let me say, shortcuts, okay, to avoid like going through this layer, for example. And their role is mainly to stabilize the training and also to make the network more efficient. So finally now, each block includes a forward like network. Like see here, this is the feed forward for the like encoder, and this one is for the decoder. So that is also followed by normalization. You see here add and norm. So and so this repeating block structure is what forms both like the encoder and decoder in original transformer model. So this is the main transformer like architecture. We have the encoder, we have the decoder, and mainly they are connected to each other through what we call cross attention. So the decoder is like multi-head attention block is going to take the encoder's output as input, okay? And this is how the model links the source sentence to the generated output mainly. And so the current trend in modern AI is mainly to follow like two stages. First, like the pre-training stage, then the fine-tuning. So in pre-training stage, mainly like we take like a transformer model, and what we do is that we train it in extremely large like data set and large and unlabeled data set, okay? So this is mainly self-supervised learning process, meaning that the model learns patterns, structures, and relationships maybe without any human provided labels, because the data set says they are massive. Pre-training can take hours or even days for powerful like computer resources. But once this stage is complete, the model, let's say, converges, and we obtain strong set of pre-trained weights. Okay. Now the next like stage after like pre-training is fine-tuning. So here what we do is that we mainly move to fine-tuning, and the data set where the data set is mainly smaller. Okay, and the training time is also significantly like shorter, so often just maybe few minutes, few hours, and just super quick. So for now fine-tuning here just like adapts the general knowledge learned during the pre-training to specific tasks, such as like, for example, translation, classification, summarization, and like so on. So from this step we obtain like fine-tuned weights, and these fine-tuned weights mainly are used during the inference at the end, okay? So thanks mainly to these two stages, pre-training and fine-tuning. So this process like allows transformers to produce much richer embeddings, like embeddings that capture context, not just isolated features. And you know the importance of context, okay? So let me move to transformer-based language models now and start with a GPT. And so, like I was mentioning earlier, in the context of transformers, there are like famous, I would say, very famous example. And mainly this is the example of GPT models, okay? And GPT stands for Generative Pre-Trained transformers. So mainly they are trained using kind of a huge amount of data, or let me say extremely huge, like large data sets, before being used for any specific task. So GPT models mainly rely directly on the idea of pre-training with massive data to learn patterns and structures in language, okay? So, yep. So now, uh, transformers or GPT now are pre-trained for very specific purpose, okay? If I provide now a sentence, like in the example here, the model is must have the ability to predict the next word, okay? So, and that is mainly based on previous one, okay? So this is one of the core application of GPT models, or so that, like, for example, just want you to keep that in mind, okay? So the application is mainly to predict next word, okay? So next word project prediction is what they like excel at. So however, like, there is also some limitations for sure, and the problem mainly now is about, it's not about like predicting the next word, but instead it's like something like filling in the blanks. So GPT in its original form will fall short, and it cannot like naturally handle missing like middle tasks. So these models are extremely like powerful and performant for next word prediction, but not tasks that require, let me say, predicting something which is mainly located in the middle of a sentence. Okay, so how do GPT models use transformers now? So as I mentioned, these like they rely on the self-attention mechanism, and which is introduced in the paper we've seen so far. Attention is all you need. And so the problem or the thing is that they do not use the full encoder-decoder architecture. Now, GPT models only use one half of the transformer. They adapt decoder-only architecture. And for BERT, they do the opposite. So, like they only use the opposite half, which means they like use only the encoder, okay, architecture. So the two architectures that we will cover today are mainly GPT, which is based on the decoder only transformer, and the BERT may be based on the encoder only transformer. So now let's start with the GPT. So GPT uses only the decoder part of the transformer, like I said. So what happens is that we completely ignore, or let me say, like completely remove the entire encoder block, okay? So all this block is gone, and if we are removing this block means also we remove the connection made like through this related or connected block. So mainly we get the essential, I would say, uh, component or elements of the decoder, okay? So this is mainly the idea behind GPT models. And so now let's mainly, like, I won't go into the internal detail here because this is like decoder, you see it, this is a decoder block, and in almost like in the previous video, like we covered the decoder, how it works and so on. So mainly it's almost identical to what we have already covered. Instead, I would move on like for second family of the models, which is like the BERT, okay? And so this is also mainly uh, using the transformer architecture, okay? And so now for BERT, okay. So BERT mainly was introduced to fix limitations that are found in GPT models. And as discussed, GPT works well for predicting next word, but it can like only read text in one direction, which is from the left to the right. Because of this like unidirectional nature, GPT cannot handle tasks like filling the blanks and, or for example, understanding missing words within a sentence and so on. So what we need now is a new model, a new transformer-based language model that could be pre-trained in order to solve tasks that are not unidirectional, and this is where mainly BERT comes in. Okay, so these are the two different uh, models, and both of them are pre-trained. So here what we say, so mainly BERT, it stands for bidirectional encoder representation from transformer. Okay, so you often heard about GPT models and BERT models, and both are simply like subclasses of transformers. So the key difference mainly is that, like I mentioned so far, BERT is based only on encoder part of the transformer. GPT is only based on the decoder part of the transformer. So although this, like, they belong to the same transformer family, each one uses different half of the original encoder decoder design, and that's depending on the task mainly. So here, like, what we do is that completely ignore or remove the decoder, and what we do is mainly keep the encoder as it is. Okay, so in this table, like, I'm trying to summarize the difference between BERT and GPT, so you will find many variations and maybe extended architectures. So now, what you maybe if you want to specialize in one topic, there is a huge amount of research, just to let you know. But for us, we need just like the key ideas. So even though GPT and BERT come from transformer architecture, the main difference between both lies in like two things mainly: the architecture, which is different, and also the training objective. So you see here the architecture, one of them encoder only for BERT, and for GPT is encoder only transform. Training direction, now for BERT, this bidirectionals use context for both sides, and GPT is autoregressive, which means it's from left to right. Meaning that in terms of objectives, BERT like masked language models like MLN predicts missing words. And for the other one, GPT, it's a causal language model like CLM, and this predicts next words. Okay, so you see the difference in terms of objective. This is what mainly we were discussing so far. Okay, there are also differences in terms of usage and contextual learning and so on. And so now, like this maybe is bringing us to modern generative AI systems. So if you want, like, for example, to summarize what is or what generative AI is. So it is essentially about giving AI models the ability to produce something new. That's it. Generate, produce something new. And means that to generate behaviors or content that look like human. Okay, so in other words, we want AI system like for example, if I ask a student to write an essay, a generative AI system should be able to do the same, produce coherent, meaningful, human-like content. And this is the core idea behind AI, okay, or generative AI. Okay, so let's return to the context where transformers are using generative AI. And so in generative AI, the goal is to create new content, like I said. And this content can be written, as we have seen, so it can be visual or auditory. So this mainly depends on the data, on the prompt, and that we provide, and many other like factors. So in this setting now, prompting like becomes the center or the main interaction pattern. So a prompt introduces a request or form of dialogue. I believe you guys are familiar with, especially we are using ChatGPT not or mainly daily. So, like in ChatGPT, for example, if you ask about question, you receive a response. Okay, so this is mainly like a prompt. Prompt is that you're asking the question. Now, in modern like prompt engineering, we can integrate many modalities. So this means that we can like use various types of input sources and not only text. So you can use also audio, images, video, and like other examples. You have so many. So generative AI tools mainly become like increasingly like widespread since 2020 maybe, and this is the AI boom. Okay, so this particular boom was driven by majority or major advancement in transformer-based deep neural networks and especially large language models. So today, many of these tools like interact with or on daily basis, and that is maybe they rely on these models. Okay, nowadays. And this introduces, like, for example, many examples that we can study, like, for example, chatbots. Like, for example, in chatbots, we can have ChatGPT, Kepler, Gemini, Claude, and so on. Also, DeepSeek. So we also have text to image, okay? For text to image, there are like models like Stable Diffusion, like Midjourney, like DALL-E, so and more. So text to video systems also, we have Sora, for example, or Veo, and like for the development of this generative AI technology, it's mainly leading to like like major companies like XAI or OpenAI or like Meta AI, Microsoft, Google, and like these companies like really like there is a development that we can see clearly. So all these systems share the same underlying brick, so that the transformer architecture is being the main thing. So I mean they rely on transformer architecture whether directly or indirectly. For example, let's say LLMs. So GPT or whatever the LLM, DeepSeek, Gemini or whatever. So this is 100% transformer based, okay? So decoder only or encoder only, decoder variants, it's like that. So text to image or image to text, video models. Here we have Stable Diffusion, maybe DALL-E, Sora, Veo. So all of these use diffusion models, but the text encoder inside, like them, is always a transformer, whether BERT or T5. Like there are many examples. So without the transformer text encoded, so these cannot understand the problem. So